Sections 3.1 and 3.2 together on vectors. So we're going to take a look at defining and understanding what a vector is, understand and calculate vector components. So what are they and how do we actually get them, using what trig functions. And then adding and subtracting vectors graphically and algebraically. And when we do it algebraically, we'll go ahead and use those vector components, and we'll do that with trig. So a vector is a physical quantity that has both a magnitude and a direction. So magnitude is the length. So from the tail to the head of the vector is usually given by an arrow, and you can add vectors using arrows and like a bit of geometry you'll see. The direction is where it's going, in what direction, so it's usually given with respect to the horizontal. So when I look at a vector, I would consider this vector, here's the horizontal. Now, if you consider where the vector starts, the origin, the easy way to think about an angle is to say that the angle is whatever happens between the vector and the nearest horizontal, which is this right here. The other horizontal is kind of over here, right? That would be like that angle right there. So the vector and the horizontal, that's the easiest way to define them. And then from there, all you have to do is say either northeast, if it's up here, southeast, down here, southwest, if it's down here, and northwest, if the vector's over here. And that's it. Just give this angle, though. So if you said, for example, 20 degrees southeast, well, I'd go southeast, and I'm pointing to this quadrant right here, 20 degrees southeast, so 45 is something like this. Splits it in half, so 20 would be like less than half of that. So that might be 20 degrees. So this might be the angle right here. Between there and there, that would be 20 degrees southeast. Again, because right here's east, and it's south of that. Remember, this is east, west, north, and south. So think about southeast, meaning you go east, and then you go 20 degrees south of it. So 15, this might be up here, like this might be like 30 degrees northeast, because you're going east, and then you're going north of east. So that's how you give your angles. So in adding vectors graphically, first of all, we have to think about the fact that we're adding two vectors together. So those vectors have to have the same units. So this might be 5 centimeters right here, and this vector might be, let's say, 6 centimeters right here. So to add these two things together, what we have to do is think about the fact that we take the tail of the second one and attach it to where the head is of the first vector. So this is the first vector here. If you literally took this arrow and slid it over horizontally and placed it right here so that this tail touched the head of this and then continued to follow the vector, it would go back to around here. So this would be where the resultant ends up. And you connect the final position where I'm pointing now to the starting position. So the resultant vector would be a vector like that, and that's the vector shown here in red. So this is like vector A, this is vector B. Vectors are given with arrows above them. And that's, we'll say, the resultant vector of that. Clearly, if you think about this, right, the vertical component of the first one, the vertical component, is kind of opposite the vertical component of the second one. So those kind of cancel each other out, the vertical parts. The horizontal component of this one plus the horizontal component of this one, when those sum together, you get a longer horizontal. So if you look at the sum of these two blue vectors right here and here, those together kind of give you this. It's all horizontal. The vertical part here and the vertical part here, those cancel one another out. So that's why this ends up being horizontal completely, because this is the same vertical component as this does. So this next image here, what we're going to notice is that we can take a look at vector addition. So we'll see what we were just talking about a moment ago, and we can go ahead and just follow our simple rules. So step one is to draw the vector to scale. So if the vector is given, you take graph paper, draw it to scale. So either you measure how many boxes up and over, or you're measuring the length of the magnitude and the angle. Here it must be up and over because there's nothing given. In the next problem, maybe it'll be given. But go ahead and draw the vector. Connect the next vector with the tail of the second vector to the head of the first vector. And then this dashed line here becomes your resultant vector. A plus B equals resultant. So draw a line from the beginning of A, which is here, again to the end of B. The angle can be measured and the size of R determined by using some scale. Scales are easy, right? This is just the hypotenuse of a right triangle. If I knew this length here, and I knew this length here, which I would for the graph paper, I could find out what R is using Pythagorean theorem. I could find out what this angle is by doing the tangent inverse of y over x, whatever that would be for that resultant triangle there. So example 1 says, a person starts to walk and travels 0.4 miles north before stopping for a sandwich. Then the person walks 0.2 miles east and breaks to read a book in the park for a while. After this, the person then travels 0.7 miles south and another 0.6 miles east. So graphically determine the person's final location with respect to the starting point. So let's go ahead and figure this out. Let's get the resultant vector and the actual angle itself as well. So we're going to draw all the vectors and connect them. So we have to go through the story kind of one thing at a time. So maybe I'll start right here. That's where the person starts, let's call that. And the person starts to walk and travels 0.4 miles north. Well, I don't know what that means if I don't have a scale. So I'm going to say that one box is equal to 0.1 miles. So 0.4 miles north is going to put me right here to end. So that's my first vector right there. After that, then the person walks 0.2 miles east. So let's go ahead and do that. It's going to end up right here. So there's the second vector. Then breaks to read a book. After this, the person then travels 0.7 miles south. So I'm going to go 1, 2, 3, 4, 5, 6, 7. 3 below where I started because the 7 and the 4 give us the 3. And then finally, the last part is 0.6 miles east. So just count over 1, 2, 3, 4, 5, 6. Ending here. Now, the question again says, graphically determine the person's final location with respect to starting point. So from starting point to final location, well, there's our resultant vector. Now to find the length of that vector, all we have to do is think about the fact that we have an overall triangle that could be a result of that. So the overall triangle, here's the height of the triangle, and here is the base length of the triangle. So really, we have a triangle that's 0.3 in the y direction, right? Well, it kind of goes down 3, so it's a vertical displacement of -3, but I'm going to say that this is 0.3 miles, and this leg is 0.8 miles. As a result, we could say simply that 0.8 squared plus 0.3 squared equals r squared, giving us an r value, if we solve, of 0.854. That's units of miles. So we have the actual length of the vector. So that's for the first part. So we know the person's position. Now the question is, what is the angle? Well, we know the angle is going to be southeast. Remember, think of your starting point of the vector right here as the origin. Draw like this as your like xy axis, or like a north, south, east, west. Well, here again is east, right? Here's south. So the angle is going to be southeast. Again, because here's east, if you go directly east from the starting point, but you went down from there, so you went south of east. So the question is, figure out this angle southeast. So if I want this angle right here, I could realize that it's the same angle as this, because these are alternate interior angles, because these are parallel lines that are cut by a transversal. So these are the same angle. Or you could simply just fill in this triangle over here. It's the same exact triangle. Right? This would be 0.8, this would be 0.3. You could find this angle here. So in theory, again, these are the same exact angles. So that is the angle we're looking for right there. That's what we're trying to define. I'm going to go ahead and find, I'll call this alpha. And I know alpha and theta are the exact same angle. So really, if I want to find the angle, I'm just going to go ahead and say that the tangent of alpha is equal to opposite over adjacent. So alpha is equal to the tangent inverse of that. And that's going to turn out to become 20.56 degrees. So in summary, the person traveled 0.854 miles at, meaning it's an at symbol, like at an angle of 20.56 degrees southeast. That would be the overall displacement of the person with respect to the person's starting position. Now let's also make another note here that if we recognize that this was really just the delta y value, this was really the delta x value of the person traveling. Right? The person did all this crazy fancy moving, But in reality, the person could have moved, right? The person could have moved this far in the x and this far in the y, or this far in the y and this far in the x, and accomplish the same ending point. So really here, when we're looking for this angle alpha, we notice that alpha was the tan inverse of 0.3 over 0.8. Well, it's the tan inverse really of this, which is opposite over adjacent, or y over x. So we could always say that when you want to find alpha or the angle or whatever it is, or theta, it doesn't matter in this case, you could recognize that it's the tan inverse of y over x. And notice I'm using the positive values of y and x because the southeast directional already takes into account the fact that it's going to be like a negative angle down below the initial side there. So if you want to, you could even put absolute values here. Okay, and you could say absolute value of y over absolute value of x. But still the tan inverse of this quantity over this quantity will give you that angle, which is the same as theta, which is what you're looking for. The next concept here is just to show that vector addition is commutative. So we'll take a look at this one, right? And we'll say, okay, we see that we have vector A plus vector B. You could follow the first path, and we end up here along that. But if we do vector B, so here's vector B, right? If we do that and take it first and do vector B, and then here's vector A plus vector A, we still end up like this with the same exact vector. So vector addition is commutative, just like addition itself is commutative. Order does not matter when adding vectors. Now the next thing we have to do is kind of the opposite of what we were doing there. We were adding two vectors. Now we have to take a vector and break it into its two components that could be. So we kind of have the result now, right? We have the vector, and we're saying what two vectors can we add together to get to that vector, right? This plus this will still get me this, but the question is, what are these vectors? Well, this is a horizontal vector, and this is a completely vertical vector. And by summing them together, we can get here. So the question is, let's find out what this length is, really. So to do that, we have to think of our trig functions here, obviously. And we can write down the following relationships. You can obviously see here that for the angle theta, we can write down our cosine relationship as adjacent over hypotenuse. And for the angle theta, we have the sine is opposite over hypotenuse. So we'll say that the cos of theta is equal to the horizontal component over vector A. The sine of theta is equal to the vertical component over vector A. So in both of these cases, what we can do is we can actually solve for the horizontal component or the vertical component by multiplying them by vector A. So take this again, right? Multiply by vector A here on this side and on this side. Multiply by vector A over here and over here. Let's move this over so we can see. So multiply by vector A here and here. Those cancel, so the horizontal component is this. And multiply by vector A here and over here. Cancel, cancel. So here's the vertical component. Now, what we're also going to notice for this is that we could always solve for that angle theta. And that angle theta, again, here, right? We could say that the tangent of theta is equal to the vertical component over the horizontal component. Right? Opposite over adjacent. So as a result, we could say that theta is equal to the tangent inverse. And in this case, we'll just say y over x, but it means just vertical over horizontal. Right? This is really y. This is really x right here. That's what that really is. So this is our relationship for the angle theta when we're looking for the resultant angle. Now let's quickly talk about the physical significance of the vector components. So imagine if you had an airplane, and the airplane was taking off, and the airplane was following this path. And at the same time the airplane was taking off, a truck was driving from that same location along the ground. And if the truck wanted to stay directly below the airplane, so when the airplane was here, the truck was right here. When the airplane is here, the truck is directly below it right here. When the airplane is here, the truck is directly below it here, until the very end. When the airplane gets to this height, the truck is still directly below it. Well, the truck would have to drive at a speed that is equal to the horizontal component of this vector. So if this vector were, say, I don't know, say the plane is flying at 200 miles per hour on takeoff. So it's 200 miles per hour is the velocity times the cosine, right? So 200 miles an hour times the cosine or whatever this angle is. Let's say the angle happens to be 60 degrees. I happen to know that the cosine of 60 is 1/2. So if this is 200 miles an hour times the cosine of 60, which is 0.5, 200 times 0.5 is 100. So if this plane is going at 200 miles an hour, then the truck has to go at 100 miles an hour, assuming this angle is 60, that is. So it's going to be a lower amount, which makes sense because the plane not only is flying, when it flies this way, it's not only flying this way, but it's also flying this way. Right? Technically, a plane flying at an angle is just flying horizontally and vertically at the same time. So it doesn't have just the horizontal velocity, it also has this vertical component, which is why this is going to be 200, and this is only going to be 100. Now, this is not necessarily going to be 100, 100, and then 200. Actually, it won't, for sure, obviously. You can use Pythagorean theorem to figure it out. But the idea is the same. Now, it's the same concept as this, and this is harder to understand. Imagine if at the same time somebody kicked a soccer ball like this, right? So a goalie punts a soccer ball, and assuming it follows that path for a little while before it starts to curl, let's say. So it follows this path. If you want to throw a baseball up, like look straight up and throw the ball up in the air, and you want the ball to follow the soccer ball, so when the soccer ball gets to this height, the baseball is at this height. When the baseball is at this height, right, the soccer ball is at the same height. And then the soccer ball keeps going, and the baseball keeps going straight up, and eventually the baseball connects and hits it. Well, the vertical velocity here is the velocity of the baseball. The velocity of the baseball would have to be the vertical component of this vector. So let's say that the soccer ball is kicked at 10 meters per second. Well, 10 meters per second, and let's say that this angle is 45 degrees. We'd have to find the vertical component. So it'd be 10 meters per second times the sine of the angle, and we said that angle is like 45 degrees. That's 0.707. So this is 10 times 0.707, so 7.07 would be the velocity of the baseball. So if I throw a baseball with a velocity of, again, 7.07 vertically, at the same time somebody kicks it at an angle 45 degrees with a velocity of 10 meters per second, then these two things would rise at the same rate. Again, although the soccer ball would also be covering some horizontal trajectory. That's the idea of the vector components. So if we take a look at adding vectors algebraically, we'll see an example of this in a minute to make it easier, but the idea here, again, is the following. So we first start and think about, we'll go back to that diagram, we start with vector A, and we specify the fact that vector A is really made up of a horizontal component and a vertical component, and that's seen here, AX and AY. And you might say, well, where did that come from? Well, AX is going to be the horizontal component of vector X, so take vector A, which is 12, it's coming from up here, times the cosine of the angle, which was 20 degrees. And again, that's up here, right? There's the 20 and there's the 12 there we just looked at. That's going to give us a value of 11.3. And then AY is just going to be 12 times the sine of 20 degrees. And that's going to be a value of 4.1. And if you don't believe me that this is true, obviously it's in the diagram, but just do 11.3 squared plus 4.1 squared and you'll get 12 squared. So if you do this squared plus this squared, you should get 144, or 12 squared, r squared. So that's the angle 20 degrees. Now, vector B also has a horizontal and a vertical component. So we have to think about its starting point here, its tail, as like a new origin. If this were like a new origin, right, look at this diagram here, to the right, how far does it go? And up, how far does it really go? So here's the x component of vector B. Here's the y component of vector B. So this length here is 12.5, this length is 21.7. If I could use the 11.3 and the 12.5 together, I can get the entire base length. And if I could use the 4.1 here and the 21.7 together, I get the entire height of the triangle. Right? Base squared plus height squared equals r squared. That's how we'll get the r value at the end. So what we need to do is find out bx and by. Well, how do we do that? So to get bx, it's the same thing as this, except there's a b here. And then this makes this 25 because I use vector b's length. Let's go ahead and do this, make it simple for us. So bx is going to be simply 25 times the cosine of, well, there's the angle, here it is, 60 degrees. And that happens to be 12.5. And then finally by is 25 times the sine of 60 degrees. And that's 21.7. So these are these two values right here. And again, 21.7 squared plus 12.5 squared will equal 25 squared, or 625. So we know these lengths, right? So we're going to go ahead and look, and we're going to add our x components together. Right? Add all the x components. So if you had 7 vectors like this in a row, you can just add up all their x components, and that's this right here. That's the resultant in the x direction, which is 23.8. Then we go ahead and add the y components together. And that's going to give me the resultant in the y direction, which is 25.8. So 2 units longer than the x component. That doesn't even matter. But what matters now is that we were able to see here that we can come up with the resultant vector in this problem. We could figure out what r is now, the resultant vector, if we do 23.8 squared plus 25.8 squared equals r squared. Okay, again, where does that come from? This comes from this last diagram right here. 23.8 squared plus 25.8 squared equals r squared. And then we can find this angle, again, by doing the tangent equals y over x. So this yields a value of r equal to 35.1. And then the other question is, what was that angle there? Well, remember that the tangent of the angle, theta or alpha, whatever you want to call it, is equal to the vertical over the horizontal, opposite over adjacent there. So as a result, we can say that theta is equal to the tangent inverse of y over x. Well, in this case, y was 25.8, x was 23.8 when we added those together, giving us an angle. We've got to press second tangent on our calculator. 47.3 degrees. So the resultant vector would be 35.1 units at 47.3 degrees north of east. Again, northeast. Here's our starting point, here's our ending point. You go east and then you go north of east. So this is the angle right here. That's our 47.3 degrees. So in example 2 we see here, John starts at the southwest corner of Central Park and walks at an angle of 30 degrees northeast for 0.8 kilometers, then stops. He eats lunch and enjoys the wonderful weather before heading 25 degrees south of east for a half a kilometer from that point. Determine his overall displacement. So we'll start with the diagram. We've got the southwest corner of Central Park here. This horizontal line is going to be 59th Street. And here is Central Park West. So the person's going to move first at an angle of 30 degrees northeast. So I want to think of an angle of 30 degrees. Well, 45 would be looking like this, right? 45 would be something like that. So 30's got to be something less than that, so I'll say that for now. So let's say 30 degrees like that. And let's say that that's 0.8 kilometers. I really don't even know what 0.8 kilometers looks like with respect to Central Park West. I don't think it makes it all the way across, though, these two segments. So for now, I'm going to just say that this is 0.8 kilometers. That's an angle of 30 degrees. Then the person goes ahead, stops, eats lunch. And then John says he heads 25 degrees southeast. Well, southeast of what? So you have to consider the fact that you need a new horizontal. Here's your new starting point. He stopped, and now this is a new starting point. So think of this as your horizontal now. So I'm going to go ahead and just draw in a horizontal here so we can see what I'm talking about. So now he goes 25 degrees southeast. So we know that it's going to be down from there. That's going to be for 0.5 kilometers, so it's not going to be as long. So this is 0.5 kilometers, and this is going to be 25 degrees. So our goal, again, as always, is to figure out what is the overall length from beginning to end, right there, from A to B, and I'll zoom in so we can see it a little bit better. So that blue line right there is what we're trying to figure out. And the other question is, what is this little angle here, right? This angle right in here. What's that angle measurement, and what's the length of this blue line? So what we're going to do again is what we did last time. We're going to take a horizontal component of this one and a vertical component, take a horizontal component of this one and a vertical component. We'll add the horizontals, we'll add the verticals, and we'll come up with our resultant vector here. So the horizontal component for this is pretty much from here to here. That's the horizontal component of that. And how do I get that? Well, I take 0.8 and I multiply it by 0.8 times the cosine of the angle. And that'll give me the horizontal component of that vector. Well, if I want to do that for the next part over here, right, from here to here now, I go from there to there. I want to get that value, so I'm going to take, instead of 0.8, I'm going to take 0.5, the length of that vector, times the cosine of its angle, and its angle is 25 degrees. Now, even though this angle here is kind of like a negative angle, it's below the axis, it's going down. So the y value is going to be negative, but the x is still going to the right. Like this x goes to the right, or this horizontal vector still also goes to the right. Whereas this goes up for this vector, right? As it's moving, it's traveling upward, whereas this one, though, comes down. So this is going to be a negative y value. We're going to see in a little. But let's get back now. So those are the two values we have for horizontals. We can come up with whatever these numbers are here, this number and this number. If we sum those two values together, we get the overall length of this triangle that we're going to make. We're going to make a triangle like this, and then back. Again, that's going to be the outline of this length here. That'll be the sum of those two. Then we'll find this height here, and then we'll be able to find the resultant as a result of that. So first we have to look at the vertical components. The vertical component of this is from here to here. How do we get that? We take 0.8 times the sine of the angle, and the angle happens to be 30. Now, we also want to figure out what the y value, or the y component of the other vector is. Well, that's going to be from right here to right here. And that value is going to be 0.5 times the sine of 25 degrees. Now, what we're going to do here, though, is we're going to take this quantity, it's positive because it goes up, and then we're going to subtract this quantity from it, or we're going to add the negative because it goes down. So we consider this a negative y vector. So you can put a negative here if you want, but I don't usually do that. I realize from the diagram that it goes down, or think about going south as negative. So I consider this to be negative. So take this quantity and add the negative value of this quantity. So let's write all this out real quick. Again, that's our diagram, though, and the diagram is really what's important here. So we've got the following. The x components, we've got 0.8 times the cosine of 30, that's 30, plus 0.5 times the cosine of 25 degrees. That's going to give me 1.15. And the units are kilometers on this. And in the y direction, I'm going to do similarly 0.8, but now times the sine of 30 to get the y component of that first vector. And then I'm going to remember either to add the opposite or just subtract the next one. Why am I subtracting this again? Because the y value is coming down. Remember, this is falling, so this is like a positive y, and this is coming back down as a negative y. So that's again times the, not cosine, the sine of 25 degrees. The same angle as the previous one, as we're seeing right here, same angle but sine this time, and the negative again because it comes back down. That'll give us a very small value. What is that? Yeah, 0.19 kilometers. So in reality, we've got a triangle, and I know this is, I'm gonna redraw it. I'll make believe this is like a new Central Park West, right? So here's the bottom of Central Park West. Technically speaking, we have a triangle that goes all the way over 1.15 kilometers, and then only up 0.19 kilometers, and then if you connect the result, and that's what it would really look like. That's the triangle we have here. So our goal, I guess, is still, right, to figure out what is the resultant vector, having, again, the horizontal, which is 1.15, and the vertical, which is 0.19. So we can go ahead and take this concept here, and we could figure out what those components are, and we could also figure out what the angle right here is between them by doing the tangent of theta equals 0.19 over 1.15. So let's go ahead and do that real quick. Okay, I'll do that right on the side over here. So we're going to end up with 1.15 squared plus 0.19 squared equals r squared, giving us r equals, and it's going to be close to the 1.15 because the 0.19 has very little significance on this when it's squared. 1.17 kilometers, yeah, very close. So that's going to be the length of the overall resultant vector, and we know that the angle theta, which is what we're looking for right here, again, theta is going to equal the tangent inverse of y over x, so 0.19 over 1.15. And that'll give us an angle of approximately 9.4 degrees. And so the answer is going to be 1.17 kilometers at 9.4 degrees northeast. How do I know that it's northeast? Simply because the person has to move to the east and then north of east. So we say northeast. Again, 1.17 kilometers at 9.4 degrees northeast.